Hello, and welcome to Solving Electromagnetic Challenges, an EMA webinar series. My name is Matt Colding, and I'll be your host for today's presentation on simulating the future of PECVD, better processes, better devices. To submit any questions you have during this webinar, please use the Teams webinar Q&A feature at the top center of the Teams menu bar. After the presentation, we will address any submitted questions. Should there be any unanswered questions at the end of the webinar today, we will address them over email. Our speaker today is Dr. Tim McDonald. Tim is a co-CEO of Electromagnetic Applications, where he has implemented new system modeling approaches to simulate the interaction of systems and their electronics with electromagnetic environments in a shorter time, with more accuracy, and at a lower cost. He is a consultant to NASA and DoD major primes for specialty engineerings of critical systems, development of novel solutions to EMI/EMC problems, and in the execution of major programs that require verification to electromagnetic environmental effects. Without further delay, I give you Tim.
Thank you very much, Matt. Imagine you're inside of $1 billion semiconductor fab. Every second, wafers the size of dinner plates are moving through plasma chambers, where invisible storms of charged particles are building the layers of tomorrow's chips. The entire industry, from TSMC's 3-nanometer logic to NVIDIA's GPUs, depend on controlling what happens inside these glowing boxes. Now here's the catch, though. The plasma sheath where the ions slam into the wafer is only a few microns thick. The Debye length is even smaller. Meanwhile, the wafers are 300 millimeters across. The chamber itself is 1 meter in size. That's an aspect ratio of 1 to 1,000,000. Trying to resolve that in 3 dimensions is like trying to simulate every grain of sand on a beach while also tracking the tides and the weather. And yet, if you don't understand these microscopic sheaths, you can't predict the ion energies, the surface reactions, the film quality. That's the difference between a perfect transistor gate and a yield-killing defect. This is the problem we set out to solve. We've built a way to bridge those scales, linking 3D plasma physics, sheath dynamics, gas flows, EM fields, and surface chemistry into a model that is accurate, efficient, and validated against experiment. What I'm going to show you today is not just another simulation tool. It's a framework that finally gives engineers predictive power over one of the most complex processes in semiconductor manufacturing, PECVD. So what we're going to talk about today first are why simulating plasmas is so hard. Then we're going to go through some of the history of plasma simulation at my company, EMA. And then we're going to talk about what industrial participants are looking for in a plasma simulation solution. Then we'll describe the innovation of Charge Plus and our pending patent. Then we'll shift into talking about validation, comparing experiment to simulation. And then we'll show simulation on real PECVD style systems. And there is a bonus topic. If you're able to stay to the end, you'll want to see that topic. And then we'll cover what's next. What are some actions you can take to learn more about these technologies and engage EMA or these products. So first, let's talk about plasmas in the semiconductor industry. So plasmas are essentially supplying the activation energy for chemical reactions in films. So the key thing are the thermal limits. So as devices get thinner and stacked, think 3D NAND, FinFET, gate-all-around, wafers themselves cannot withstand repeated high temperature steps. It makes sense, right? As they get smaller, it's hard to survive that big temperature. PECVD, which includes the plasma, allows us to deposit at 100 to 400 degrees C. That's in comparison to thermal CVD, which would be greater than 600 degrees Celsius. And then conformal films, when we want to have aspect ratios, which is the height to width ratio. When they become very large, think trenches or vias with aspect ratios of greater than 5:1. Uniform film coverage is a difficult thing to do. PECVD, as well as other type of techniques like ALD, give us better control of sidewall and top coverage. Stress engineered films is another consideration. PECVD enables tuning of dielectric stress to strained silicon channels. This has been used since 90 nanometer and smaller nodes for mobility enhancement in those particular channels. PECVD is essential for advanced semiconductor manufacturing. Think smaller than 16 nanometers. First, interlayer dielectrics. These are used for insulating films between metal layers and back end of the line. Low K dielectrics are commonly deposited using PECVD technologies. Next, we need to think about impassivation and encapsulation. SiN and SiO2 and other protective layers are PECVD deposited to protect devices from moisture, ions, and mechanical damage. Hard mask and etch stop layers. PECVD, SiN, and SiCN layers define etch boundaries and stop layers for dual damascene copper interconnects. Advanced packaging and 3D integration. Wafer level packaging, TSVs, through silicon vias, and fan-out structures all require conformal PECVD films for insulation and protection. Why do we want to bother with physics-based simulation? Well, the key is process optimization without trial and error. Semiconductor fabs are astronomically expensive to run. Running thousands of wafers through try and see experiments wastes time and money. Simulation allows engineers to tune gas chemistry, plasma power, reactor geometry, and flow conditions before risking expensive runs. Understanding plasma surface interactions, the plasma generates ions and radicals that interact in complex ways with wafer surfaces. Simulation allows you to see how the film growth rate, uniformity, and film quality depend on these interactions. And then the next consideration is scaling reactor designs. Next-gen PECVD tools must deposit uniformly across large wafers, 300 millimeters moving toward 450 millimeters. Simulation helps predict how chamber design, such as the shower head, pumping ports, electrode spacing, affects uniformity across such scales. And then we need to think about new materials and structures. As the industry moves beyond SiO2 and SiN into low K dielectrics, high K layers, and novel 2D materials, experimental knowledge is limited. Simulations give insight before committing to costly hardware development. Another reason that simulation is hard is the physics itself. So the plasma behavior. Plasmas are sustained by RF or microwave electromagnetic fields. So this requires solving Maxwell's equations with charged particles present. And those charged particles need to be able to respond on nanosecond timescales. So that means your time steps need to be picosecond or maybe even femtosecond timescales. We need to consider plasma kinetics and chemistry. There's hundreds of species, including all of the permutations of ions, radicals, metastables. They all participate. And each has reactions with different cross sections, rate constants, and dependencies. It often requires using Monte Carlo combined with particle and cell methods, which are themselves computationally expensive. The gas flow is solved itself with fluid dynamics, and the neutrals move with viscous and sometimes rarefied flow regimes. And you have to couple the Navier-Stokes equations with the plasma source terms in the chemical reactions. And then we have to think about the surface reaction and film growth. Film deposition depends on sticking coefficients, recombination probabilities, surface diffusion, and microstructure evolution. These occur at the angstrom to nanometer scale, but they've got to be simulated over the wafer dimensions, which, as we said, is hundreds of millimeters. And so it makes it a multi-scale problem. The spatial scales go from angstrom level film chemistry to the 300 millimeter wafer up to the 1 meter reactor chamber. And then we also have time scales. The temporal scales are femtosecond electron motion to microsecond plasma oscillation to the seconds to minutes process times. Bridging these has in the past required several approximations and hybrid models, fluid, kinetic, empirical. As a result, up until today, almost everything has been reduced order models, which means going from 3D to 2D, simplified models, or empirical models based on experiment. This is something that we need to advance, and as time goes on, we need new technologies. So who are we? Who is my team? So EMA as a company was founded in 1978 to study nuclear weapons effects on strategic systems. The Cold War ended in 1991, and EMA adjusted our focus to commercial applications of electromagnetics. That includes full physics, simulation of arcs, discharges, ESD, and lightning effects. In 2007, EMA started supporting space plasma interactions on spacecraft and quickly became active in all major U.S. human spaceflight missions, including the Artemis Orion program, and as well as many satellite programs and satellite constellations under development and currently deployed. Then in 2020, EMA announced Charge Plus, which is a new general approach that we're going to talk about today without approximations or empirical models. And we also created the EMA Space Environments and Radiation Effects Lab. And this gives us a place to do plasma physics empirically. So a key thing to know is that EMA is an ANSYS, which is now part of Synopsys technology partner. And we're also an ANSYS services partner. So that means that the technology we develop, like Charge Plus, can be sold by ANSYS and ANSYS channel partners worldwide. Currently, EMA has 80 staff. We're headquartered in Greater Denver. We have 6 facilities in 3 states, and we are available to support your challenging semiconductor applications. So specifically with the technology, what is industry asking for? Essentially, customers want to be able to properly characterize the ions and electrons incident on the wafer substrate, making it through that sheath. The key quantities that they care about are the angular distribution functions, or ADFs, and the energy distribution functions, or EDFs. And they need these for both electrons and the key ion species that are going to be participating in the chemical vapor deposition or the other processes. PECVD chambers themselves include multiple substrates. You could see in this animation happening above that there's 5 surfaces that we're seeing. And so the flow is going by those multiple surfaces. And so you really want the ADF and the EDF for the ions and electrons at each surface so that you can apply them on follow-on models that are looking at what's happening to those individual nanometer or angstrom level processes. What else does industry want? So as I mentioned, this really needs to be a 3D flow problem. So we need to be able to capture 3D flow from an existing mature Navier-Stokes solution, such as ANSYS Fluent, and take that as an input for the coupled co-simulation. The co-simulation itself needs to have its own Navier-Stokes solver. But once you include the plasma, it's going to be solving on a much shorter time scale than the 3D flow. So we want to pull 3D flow as an input and then solve in a hybrid way once we've pulled that input in. So why do we want that? Or why does industry want that? First, that neutral gas flow controls the plasma uniformity reactant supply. So those neutral gases that come in the chamber through the shower heads, they're carrying the precursor molecules, silane, ammonia, oxygen. If the flow is uneven, some regions may get more reactants than others. Depletion effects at high aspect ratio or large wafer processes. Precursors get consumed along the way. Poor flow distribution means the center of the wafer may see different chemistry than the edges. And then residence time. Gas velocity affects how long molecules stay in the chamber, influencing dissociation rates, byproduct buildup, and overall deposition uniformity. Without modeling the 3D flow, you just can't predict these local concentration differences that directly affect the film thickness and quality. But the other aspect we need to think about is the co-simulation. So the electromagnetic field asymmetry will affect the plasma density. And the plasma itself is sustained by RF and microwave fields. Their distribution depends on the chamber geometry and boundary conditions. If the electromagnetic fields are not symmetric, the plasma density will vary spatially, giving you uneven ion bombardment on the wafer and non-uniform radical generation in the gas phase. The gas flow interacts with the plasma, so a full 3D coupled model is needed to capture these effects. Next, we want to think about localized heating that alters the chemistry and flow heaters and the RF power absorption or hotspots. That can create temperature gradients. So the gas temperature effects, reaction rates, the Arrhenius dependence, the gas density. Hot gas is less dense, altering flow patterns. The fusion rates of radicals and byproducts. These thermal asymmetries cause both neutral gas flow and plasma kinetics, feeding back into deposition uniformity. So it really needs to be two-way coupled problem. After we've solved the computationally expensive coupled plasma and fluid flow, we need to feed that data back into a fluid solver, such as ANSYS Fluent, to capture some of these longer timescale effects. And then finally, the consequences for process control by coupling the simulation together. When any of the above effects are ignored, you risk non-uniform film thickness across a 300 millimeter wafer or larger. You could have variations in film properties, such as the refractive index, stress, stoichiometry. You could have reduced yield in production due to edge versus center differences. You could have scaling failures when moving from small research reactors to full 3D scale or full-scale production tools. That's why we say at EMA that the three-dimensional modeling is not just a nice-to-have feature, but it's essential. We need 3D for the chamber, the wafer, the plasma. They're all inherently three-dimensional. And because the industry has been using 2D or simplified models, they're often missing these critical asymmetries. So that's the reason we put so much time and bear the computational expense of going for full 3D. The next thing is we need to include two frequencies for the RF excitation to the plasma. When we're doing PECVD, the dual frequency RF excitation is one of the knobs process engineers use to control the PECVD plasmas. Modeling it's important because the two frequencies act on different parts of the plasma in different ways, and that interaction is nonlinear. Let me explain. First, we have independent control of the plasma parameters. The high frequency side, for example, 13.56 megahertz or higher, that couples primarily to the electrons. It sustains the plasma and controls the plasma density. Then there's a low frequency component, which is 400 kilohertz to 2 megahertz. That couples more strongly to the ions and modulates the sheath potential and thus the ion energy at the wafer. Remember, the name of the game here is to figure out what ions are getting through the sheath and the way they get through the sheath. So by combining control of the high frequency and the low frequency, engineers decouple ion flux, the density, from the high frequency ion energy. Without modeling, it's really hard to predict how this balance is going to play out. The next thing is the nonlinear interactions. So the plasma sheath responds dynamically to both frequencies at once. It's not as simple as just doing superposition because the sheath thickness and the potential oscillate in a complex way. This leads to nonlinear ion energy distributions that strongly affect surface reactions. Modeling is the only way to capture these time-dependent, frequency-coupled effects that also depend on the magnitude. So the third is impact on the film properties. Film density, stress, and hydrogen content and PECVD layers all depend on the energy and flux of ions striking the surface. If you have too much energy, you could cause damage, re-sputtering, or stress. Too little energy can lead to porous, low-quality films. Dual frequency is what lets engineers tune precisely, but only if they understand, ideally via modeling, how both sources shape the IED. And then we have spatial and scaling effects. As we've said before, in large area reactors, for example, 300 millimeter wafers or displays, the field distribution from dual frequencies may not be uniform. 3D modeling helps us predict if standing wave effects that happen from the HF source. It gives us asymmetries and ion bombardment from the low frequency source, and we could get edge versus center deposition differences. The next thing that the industry needs is the plasma sheath. So what is the plasma sheath? When a plasma touches a solid surface like a wafer, electrode, or chamber wall, a special thin layer forms at that boundary. That layer is called the plasma sheath. Why does it form? The difference is the difference in the mobility of the electrons and the ions. Electrons are light and fast. They move much quicker than the heavy ions and respond more readily to the electromagnetic fields. When plasma touches a surface, electrons are the first to hit it and can escape from surfaces more easily. The surface then quickly becomes negatively charged compared to the plasma. This charge imbalance sets up an electric field near the surface. That electric field repels most electrons and attracts positive ions. The result is a thin boundary region, and we call that boundary region the sheath. The key features are the thickness. In this density of plasma, in this type of plasma, the sheath is very thin compared to the overall plasma. It's measured in microns versus the overall plasma is measured in centimeters. The sheath acts like an insulating skin between the plasma bulk and the surface. And the sheath directs positive ions toward the surface, high energy. Why does it matter in PECVD? The sheath controls how ions hit the wafer. Remember, that's the name of the game. And the ion energy determines how dense and smooth a deposited film is, whether a surface gets cleaned, etched, or damaged. Engineers tune the sheath via the RF power, the RF frequency, etc., to control the film quality. Now I'm pleased to announce EMA's technical innovation in this space. It's a product that we call Charge Plus. And this is our new 3D CAD integrated simulation tool for RF plasma discharges with multi-solver interface. We have a pending patent that we've applied for, which, if approved, will mean this is the only place that you'll be able to get this type of method. So ANSYS Charge Plus is integrated multi-physics for plasma simulations. So in this product, we are solving the time domain electrodynamic equations. They're solved on an FEM basis using the potential formalism, and those equations are solved in the time domain. And we couple that with a particle and cell solution. If you're not familiar with PEC, it's easy to imagine because this is the most brute force, low level method to solve fluids or kinematics. Imagine literally particles that move in 3D on a 3D grid that represent each particle is an ion or an electron. And it represents, they're called macroparticles. Each macroparticle represents many, many electrons or many, many ions. And by tracking them and their path in 3D, you can track the forces that are imparted on them and then feed back to the overall FEM or to the other fluid solver, which brings us to the other fluid solver. We need to co-simulate with a full-fledged computational fluid dynamic Navier-Stokes solver. And this allows us to solve the neutrals or the ions. We can put any species we want in either the particle and cell or the CFD and have them interact with each other. This is a big deal. And in order to connect with other fluid solvers as a initial first step, or after we finish the plasma simulation, we need ourselves to have a fluid solver that will make that communication with that third-party solver more accurate. And then finally, I haven't mentioned this before, but we have to think about reactions. In the PIC, I'm going to talk about a moment about how we do that, but essentially we need to consider the cross sections for those reactions that happen in the plasma phase, because there are many in any plasma. You're going to have all permutations of all those radicals that are formed and those that can form through ionization or dissociation in the plasma itself. Another key thing about this technology solution is the interface. So this is a brand new product. It has a modern CAD interface. It has been built to make it easy for users to specify the species, which type of fluid solver they want to solve each species, the way that users want to add all of those chemical reactions, they're captured here so that they can be carefully input. And of course, all of this can be automated by APIs so that we can get to the point of automation, and you can control this with other tools outside of this tool, but it's also built for a user interaction mode. I mentioned the chemical reactions that happen. So essentially, one of the key innovations that we have is a reaction solver with particle and cell and Monte Carlo collisions. So that's PECVD. So what is going on here? So the reaction solver with PECVD provides a self-consistent way to simulate particle transport and interactions in the plasma. The reaction solver determines particle scattering and collision events probabilistically based on the underlying plasma parameters and cross sections. So with the particle scattering, we've got the collision probability. So each particle's chance of undergoing a collision during a time step is computed from its velocity, the density of the background gas, and the relevant scattering cross section. And this cross section is what I'm showing. This is a nitrogen cross section. You can see there's all many different types of radicals that you see, and cross sections as you see just for nitrogen. Randomization. So a Monte Carlo draw is used to decide if a collision occurs in the current time step, and this ensures that the scattering events are stochastic while maintaining the correct average collision frequency. Then we've got the PEC time step dependence. The scattering probability is scaled by the time step, meaning shorter time steps reduce the likelihood of collisions per step, but maintain physical accuracy over time. And then we have to combine that with energy and momentum conservation laws. So collisions are modeled to conserve the total energy. And we've got velocity randomization. After a collision, the particle's velocity direction is randomized to reflect scattering angles. And this mimics real-world scattering while preserving overall kinetic constraints. And then we've got continuum scattering and ionization. So first, the continuum scattering. This describes elastic scattering processes where the incident particle is deflected but remains in the same energy band. For example, electron-neutral elastic collisions. Also, ionization cross-sections. At higher energies, collisions may result in ionization. The solver uses tabulated or fitted cross-section data to determine the likelihood of ionization events, which then creates secondary charged particles. So our plasma, the number of species in the plasma may grow due to the ionization that happens from the fields. And then we've got decoupling, or the coupling to plasma dynamics. This is ionization processes that feed back into the plasma density and the electric field evolution. And that makes the PEC-MCC solver fully self-consistent. So as you can see here, just a few of those scattering cross-section equations are listed there. Another innovation that EMA has done, and this is a very important one, is our energy conserving semi-implicitization scheme. So we can see what happens without implicitization, and we're showing temperature on the left, and basically heats up. It's runaway. It shouldn't be doing this. Why is it doing this? It's something called numerical heating. So how we get over this is with our EC-SIM capability. In a particle and cell finite element method framework, the particles represent the plasma species, of course, and the FEM grid solves the fields. Shape functions are the way we interpolate between these two representations. So what that does is that deposits particle currents to the grid and then interpolates fields back to the particles so they can see and respond to those fields. If the shape functions aren't good, interpolation errors cause numerical heating. This is what you saw in that image there. That's artificial energy gain from the grid, and it just runs away. The temperature blows up. You could get inaccurate field particle coupling or loss of energy conservation, and that's key. So what we do to improve that, we do accurate interpolation. So they're better shape functions, and they ensure current field interpolation is consistent and stable. And this leads to better representation of particle field interactions, especially in regions with steep gradients like sheaths. And then we have implicitization to handle the Debye length limits. So traditional PIC requires mesh resolution smaller than the Debye length, which is very small in this dense of a plasma. And that can be extremely demanding. It may not be computationally possible. So our semi-implicit scheme relaxes this requirement a little bit, preventing numerical heating, even when our spatial steps are large, and it allows us to do that without losing accuracy. And then exact energy conservation. This gives us a semi-implicit exact energy conservation algorithm. The current from the PIC particles deposits the FEM. The FEM then corrects the electric fields used to push the particles. This closes the loop and ensures that the energy exchange between the particles and fields is always physically correct, and it helps us avoid spurious growth or damping. The benefits for the PECVD plasma modeling helps it be stable on long-time simulations without artificial heating. So you can see in this, with the implicitization, we don't see the runaway in the temperature like we saw in this curve. It gives us accurate sheath resolution when coupled with our subcell sheath model. And it gives us, and I'll talk about that in a moment, it gives us confidence in predicting simulations because the numerical framework respects conservation laws this way. All right, the next innovation that we've added is to add a charge plus circuit solver. So this is a SPICE circuit that co-simulates, and that SPICE circuit basically can become your boundary condition. So as we know, PECVD systems, they're basically an RF or microwave source, and there's a matching network on the electrodes. The plasma itself, as we said before, is nonlinear and time varying. That means the actual fields inside the chamber can't be done with EM simulation alone. They depend on the circuit that drives them. So now we have the ability to have a general circuit applied as that boundary condition, because as we said before, the knob that engineers turn is the power applied to the different RF frequencies. Without a circuit, you can't apply a power boundary condition. Next, let's talk about 1D sheath modeling and it being analytic as well as a kinematic version. So why do we need this? The sheath region is extremely thin compared to the bulk plasma, and accurately resolving the 3D sheath requires very fine adaptive meshing. We've said before that getting the ions going through these sheaths, that's what we're after. That's the name of the game. But if the sheath is tiny and we need to do micron-sized cells, that's very computationally expensive and maybe impractical in some cases. But sheath physics is critical. Without it, we can't get the ion energy, flux, and surface reactions, which directly determine our deposition etch outcomes. So what we've done is we've introduced subcell sheath algorithms at every surface element to properly capture sheath behavior. So you've got two options, an analytic and a kinematic. The analytic version, each finite surface element gets its own localized sheath model. A sheath is divided into a finite difference subgrid, and it's solved on a nonlinear Poisson equation in 1D. And this enforces the asymptotic boundary condition that matches the sheath potential to surrounding bulk plasma potential. It gives us more accurate results than adaptive meshing would in the bulk plasma by itself. We also have a kinematic sheath, and this extends the accuracy further with a particle and cell 1D algorithm at each surface element. It captures the ion and electron kinetics in the sheath, not just the fluid analytical behavior. What this gives us is detailed modeling of surface reactions within the sheath context. So the key benefits here is we avoid full 3D ultrafine meshing, and it reduces the computational costs. We know that capturing sheath physics is critical to film growth and surface modification. So this can make that accurate even without superfine meshes. And it's localized. Each surface element gets its own sheath solution. And that gives you an asymmetric reactor geometry and non-uniform plasma conditions. And it's flexible. It supports both analytic approximations or the kinetic or PIC treatments, depending on the accuracy or performance needs that users want. All right, that's the innovation. The next question, and everyone should ask next, is that sounds great, but can you get the right answer? And that's a complicated question because in this field, recipes, results are highly proprietary, highly sensitive. Luckily, there is a forum for collaboration, and that's the Gaseous Electronics Conference, or GEC, and they have a standard reactor that uses argon plasma. It's not necessarily an industrially used plasma. in this field, in this case, but it's something that can be used for validation and you don't have to give up the sensitive details. So the good news is that Charge Plus can absolutely get the GEC reactor and it gives perfect results. So we can resolve that. So you can imagine we're seeing just a cross section. So if you look at this location with the higher electron density, it looks like a donut. It's going to wrap around the reactor cell with this maximum area. And if we compare the end regions, we can see the electron distribution will match up with the experimental results that we know about. And then we can look at all the different aspects. There's so much going on in plasma. So you can plot things like the potential, the ion temperature, ion density, the electron temperature, the electron density. This is using full PIC in this case. It's at 0.25 torr. It's run on not a very aggressive CPU. You can run this demo on a laptop with 6 cores. This is 11,680 mesh elements. We're doing 100 cycles. So actually, that's when I say cycles, I'm meaning RF cycles. So we're actually taking it to the point where we're getting close to equilibrium, and it runs in 12 hours on a laptop. So you can imagine accelerating this on bigger hardware. You could do much better than that. And the validation results, the potential overlaid with the publication just absolutely match up. And then the radial density distribution absolutely matches up. Okay, we can do the GEC cell, but what about real world application examples that are more like an actual GEC cell? So let's talk about that. So here we have this user demo. You can download this user demo. You can try it yourself. This is a dual capacitively coupled plasma, dual CCP with using our circuit boundary condition option. And so you can see very clearly in the potential, we're seeing both the high frequency, the little wiggles, and the low frequency. And we're getting 2 full cycles of the low frequency. You can see the potential is getting quite high. However, we're getting through 1 low frequency cycle in 24 hours, on the order of 250,000 mesh elements. We've got 1 million macroparticles in this case. And this simulation, when we look at the animation, it stays stable. And so this is, if it was going to go unstable, it would have already gone unstable by the time we get through 1 or 2 cycles here. So we proved we can stably do this industrially relevant plasma. But what does industry want? What are they after? We alluded to this before, but what you want to do is track the ions going through the electrode. So up here is the electron momentum density, and down here is the ion momentum density, the chips on the top of the chamber. And so you can see we're tracking the momentum of those ions hitting the chip or chips themselves at the top. And that's going to give us our energy distribution and our angular distribution. And that's industrially what people are using are tools like Centaurus Topograph that is doing the trench deposition simulation, and you get that information that you need as inputs for this tool from Charge Plus. So that's huge, and that's what people want to see. And we can do with this tool the coupling back and forth to the CFD tools like Fluent. So we can see how the 3D flow is going to change the processes, because we're running, after we get that initial condition from Fluent, we're running our flow self-consistent and also our solver with electromagnetics, CFD, and PIC all running together. So in a chamber, you can see here where we've got 5 different surfaces. The question is, how is that going to change? We've got the ADF and the EDF for surface 1 versus surface 5. You can clearly see there's a difference. And if you look in the time domain, when does that change happen? It actually happens pretty early in the process. We're around 1 microsecond, and you can already see it's starting to diverge for those different surfaces. So we can already get you the ADF, EDF information that you want. We can do this starting with an initial condition from your fluid solver, and then we can run self-consistently coupled with CFD. They're actually quite industrially relevant timescales and start to see the differences that are happening. So That is the innovation. That's what we've developed. So very happy to be reporting that today. Okay, I promise one more thing. So we're more than just a company that provides development of software like Charge Plus. We also have a big services and a testing team. And so we have been doing plasma physics for several years now. We can measure quantities like secondary electron yield off of surfaces of different materials. We can model how different materials perform in plasma environments. And very soon we'll be able to measure some of those ionization cross sections that we talked about that are critical inputs for this process. So if you want something measured to characterize materials or to characterize plasma chemistry, you can come to us. If you want help with the simulation, it's a big thing to get into the simulation. It may make sense if you're getting started to engage our services team to run some of these sims for you and help get it set up and teed up, get your team trained. So we have a full team, more than 50 services engineers that can help you with whatever you need. So finally, call to action. If this is interesting to you and you would like to learn more, I would encourage you to get on the EMA website. So our company website is ema3d.com. You can click the Expo link, or if you want to go to it, there's the link right there, EMA Expo 2025. There are YouTube videos going through the PECVD and plasma simulation technology, so you can go deeper, learn about some of the fundamentals of the solver itself from the developers themselves, as well as some of the engineers that have developed this technology. So get on there and learn more. What if you would like to try out this software? This is commercial software. This is available to be purchased. Again, it's typically sold through the ANSYS or the ANSYS channel partners. If you would like to get a demo, reach out to John Twerdock at ema3d.com. He will connect you with the appropriate ANSYS or ANSYS channel partner for your region and your company, and you can ask about that demo trial and get your hands on the software. Finally, if you would like to engage our services team, that's a great way to get started. If you want us to perform simulations, or you want us to do some measurements of materials or some plasma or gas chemistry, reach out to Matt Colding at ema3d.com and he will get you set up with that, which is a perfect segue now to Matt Colding.
Thank you very much, Tim, for such an informative presentation. We can transition into the Q&A portion of the webinar. So as a reminder to all the attendees still watching today, you are encouraged to submit any questions you have to the team's Q&A feature. While we wait for any questions from the audience to get submitted, I did have a few kind of common questions to help our audience understand how EMA's services can help them. So the first thing is, how can EMA's services team help customers get started with this kind of analysis?
Yeah, so in many cases, customers have scenarios in their PECVD chamber or examples of what they have tried to model with other tools, but are limited to being in 2D, or maybe they just know the scenario that they want to model, but they don't know how to get started. So what you can do is you can contract the EMA services team, and we can model that very first case scenario for you. So we'll build the model, but we'll build it on the commercial product. So when we're done, we'll give you that model we built of the scenario you wanted to model, as well as you can get the commercial software, and then you can run it yourself. We can train you how to do what we did. And that's a great way, and probably the most common way that companies get started is from that simple services engagement like that.
Great. So does a customer need to have everything scoped out ahead of time before they contact us?
That is something that we can work around. So what we can do is create a level of effort type of contract with the ceiling. And so it could be something that fits the budget of your team, and we can get started in preparing that simulation alongside you, and you'll have full control to manage what we do, how we do it, and you don't have to know all that ahead of time. So that gives you flexibility, it limits your risk, and lets you get exposed to the technology without a big upfront financial commitment.
Excellent. Another question that I get commonly is, how can customers book services in our lab? Is it very easy to engage?
Yes, so this is a commercial plasma lab. So we created this because in the past, many customers, including ourselves, were having to go to academic labs, which are great, doing great research, but the mission of academia is to publish papers, which can be a problem if you want to control some industrial secrets, as well as sometimes the academic cycle for doing a test that you need done doesn't match up with your need. You probably want it done right away. So we created the plasma testing group and purchased the plasma chambers so that they could take advantage of our ability to protect industrial secrets or government secrets. EMA is a cleared facility. We could take advantage of EMA's ability to be more responsive. For example, if you come to us and tell us the timeline you need something tested, we can work with you to make that happen. And in many cases, that's going to be a much faster timeline than an academic or government plasma lab would be able to respond. And then also, who wants to test on their competitors' systems, or maybe a critical supplier that may use that against you in the future. So we're a neutral party. We're not involved in the industry outside of doing simulations and testing. So if you want to protect some of those industrial secrets and not work with competitors, you can work with our team and we'll protect your data.
Excellent. So I'm not seeing any other questions in the Q&A queue at the moment. So if there are no other questions, maybe we could wrap up with kind of a final statement from Tim. Is there anything else that you'd like to say to the audience today?
Yeah, it's been an exciting journey with plasma physics at EMA for the last few years, but we're not done. This technology is evolving. We're growing our team to make it better, and we want to be responsive to your needs. So please reach out to us and help us understand how we can, what the challenges you're facing, and help you understand if some of these technology may be helpful to you.
Excellent. Well, thank you very much, Tim, and thanks to everybody in attendance today. I think it's now time to conclude the session. So as a reminder, following the conclusion of the session today, all registrants will receive an email from EMA with a link to the recording of this presentation, as well as a PDF copy of the PowerPoint that Tim covered this afternoon. If you have any questions about a particular section of interest to you, please feel free to respond to that email or through either any of the call to action channels that Tim has provided here. Next up in the EMA Solving Electromagnetic Challenges webinar series is the integration of ANSYS EMC Plus, SI Wave, and HFSS, which will occur on October 22nd at 11 a.m. Mountain Time, 1 p.m. Eastern Time. Thank you all very much for your time and attention, and I hope you have a great rest of your day.